Good afternoon, everyone. Today, what we're going to do is hopefully this will be a shorter lecture, and then in a separate video, I will try to do a little bit of review in preparation for your test 3, which will be held this Friday. Now, along those lines, I would like to remind you to read the email that I sent around, I believe, yesterday regarding test 3. It will now be open at 3:45 p.m. So I'll just write this again. Test 3 on Friday. And it will start at 3:45 to 5:45 p.m., at least having the release of the test. This is just to give everybody extra time to deal with any technical issues that may come up, particularly, and also hopefully this covers the time for those of you who are writing with SAS. My main reasoning for the timing was that the test is supposed to be at 4:30, so if you already set aside time to do it for 4:30, you should still be able to download it at 4:30 and upload it the same way that I've been saying before. And if you're writing with SAS, then the thought is you can download it earlier and get a head start so that you still have time to upload before the due date or the deadline. And so what you'll need to have access to is your email, because the CrowdMark link, it will be there. And as well, you need access to your, paper and phone or scanner. That should be 2 N's, to upload your responses. There are a number of students who have provided some of their feedback on the discussion board. What it seems to be is that those who have scanners, some of them, they generally scan maybe a bit slower when you're doing it page by page. So it might, even if you have a scanner, you might find that using your phone, if you can, is easier. Those who have tried the Cam Scanner app found it very easy to upload it, at least from what I've heard. But then even if that seems a bit too much, some have also taken to just taking pictures and uploading the photos. What you should note, though, is that as far as I know, photos need to be JPEG, not PNG files. Okay, and so it should be able to PDF files and JPEGs should be fine. Now, if you try something and it uploads to CrowdMark, then we're fine. I don't really care what format it is. The main thing is that it's up there, and hopefully that it is readable. That will make it easier for the TAs to grade as well. And last resort, if you have any problems, email me. Okay. But hopefully that this should go okay or run pretty smoothly. I know a number of other faculty that have used this in their courses as well, and I haven't heard any big complaints from them either. So I'm hoping that this is I know it's be stressful if you haven't done it before, but then I would suggest you actually try uploading something in the mock test just to give yourself an idea of what's involved to upload your responses and how much time will be needed. It's recommended you try doing that before doing the test, particularly if you're stressed about that. Okay, so today what I wanted to do was talk about logistic regression, and I don't think we'll quite get to how you interpret model parameters, but we'll leave off, I guess, just before we get to that point. So when we were dealing with multiple linear regression or simple linear regression, we had a response that was continuous. But sometimes we think even though our response is maybe binary, so we might have a y that is coded as 1 if there's a success, whatever that success means, and 0 corresponding to a failure, we might still want to relate that success or failure status with some other explanatory variables or predictors. So how do we go about doing this? Well, one thing is to note that the mean of y is p, where p is the probability of success. Okay, so just to remind us, the expected value of y is going to equal all values of y that can take on, and it can only take on 2. So we have 0 times the probability y equals 0 plus 1 times the probability y equals 1. So this first term goes away. We don't need to worry about this coefficient because it's a 1. So p is just equal to the probability that y equals 1, which is a success, and that's the mean of y. Now, if we want to relate this to some binary, to some explanatory variables, you might think, well, let's just set p equal to beta naught plus beta 1 x. But there's a problem. Our probability lies between 0 and 1. And then when you put in an explanatory variable that may take on any value, then it's quite easy to see that sometimes the predicted values from that regression model might be negative, or it might be greater than 1. So in other words, the predicted values from the regression model might fall outside the 0-1 range. So what do we do? Instead of using the mean of y itself as the response, we would use a different model that's a function of that mean response. So the model that we use is based on the log odds. Remember last day we talked about how the odds are equal to the probability of success divided by 1 minus the probability of success, or the probability of a success over the probability of a failure. So when we take the log of that, this is known as often termed the log odds, but it's also known as the logit function. So sometimes you might see this written as logit p. I generally won't do that, but that's where the term logistic regression comes from, because our response is based on the logit of p. So it's a function of the mean of our response variable. So let's start off by looking at a simple logistic regression model. In a simple logistic regression model, remember simple corresponds to there being only one random variable. So it says, let's take the log odds, and it says, okay, we're going to describe the log odds in terms of a straight line, beta naught plus beta 1 x. So we're essentially saying that the log odds has a straight line relationship with x. And this x variable, it may be continuous or it may be binary. The first example we'll look at, x is going to be a binary random variable. And what we also have to remember is that this log, and that's what's written in your textbook as well, is the natural logarithm. So later on you'll see that I'll switch to saying ln just to remind us, but the log generally in statistics, log always means the natural logarithm unless otherwise stated. So if x is binary or is an indicator variable, What's nice about that setting is that we can actually find explicit estimates for beta naught and for beta 1. So let's do that. Let's look at an example. And what we'll do is revisit the SALT and cardiovascular disease data that we looked at way back in chapter 9. So remember, we had subjects who were either on a low salt diet or a high salt diet. And at the end of the study, they were checked for whether they developed cardiovascular disease or they did not develop cardiovascular disease. And so what we might be interested in doing is saying, okay, well, what's the odds of developing cardiovascular disease? In that instance, we need to first calculate the probability of developing cardiovascular disease. So among this low salt group, we see that 88 of them went on to develop cardiovascular disease. And in total, there were 1,169 subjects that were on that low salt diet. So if we take the ratio 88 over 1169, we get 0.075278015. So this is equal to the probability that CVD is equal to 1 when the salt level, so I'll just put salt equals low. And by the same token, if we look at the probability of cardiovascular disease in the high salt level group, so pH high, we can see that we have 112 of them out of the 1246. So that gives us a probability estimate of 0.089887764. And this is equal to the probability that CVD is equal to 1 when the salt level is equal to high. And then if we want to calculate the odds, just like we saw last day, we want to take the ratio of p hat over 1 minus p hat. So for the salt group, that's our p hat. For the high salt group, for the low salt group, and for the high salt group, here's our estimate. So when we want to calculate the odds, we have the probability of estimate of p hat low over 1 minus p hat low. So that's the ratio, and we end up with an odds of 0.0184, etc. So this is the odds of CVD, of developing cardiovascular disease, for the low salt diet group. And for the high salt group, we can do the same thing. We get 0.0987. So this is the odds of CVD for the high salt group. And now we're in better shape to be able to go through, fit a logistic regression model, and actually estimate our model parameters as well. So in order to formally do that, let y, our response, be a binary variable that takes on the value 1 for those who actually go on to develop CVD, and 0 for those who do not develop CVD, the cardiovascular disease. And we'll let x also be an indicator variable for the salt level, where 1 indicates being on the low salt diet group and 0 is being on the high salt diet group. And you might be wondering why we did it this way. As usual for indicator variables, it's somewhat arbitrary, but in this particular example, remember that the big picture thought process was that a low salt diet may help prevent cardiovascular disease or may lower it. So in that sense, the low salt diet is kind of like the treatment. So the X is equal to 1 if you're on treatment, 0 is if you're on the control, where the control is considered to be that high salt diet. Okay, so let's look at our logistic regression model. And what it does is, remember, it takes the logit of p, so log of p over 1 minus p, sets that equal to beta naught plus beta 1x, so that's our straight line relationship. And in the population, let's see how this relates to our salt and cardiovascular disease example. So there we had a binary variable. When x equals 1, then we're talking about those who are on the low salt diet. And what we found, what we see is that the ln of p for the low group over 1 minus p, so the odds for the low group, is equal to beta naught plus beta 1. So we can also remind ourselves that too. This is ln odds for the low group. And when x is equal to 0, we're talking about the high salt group, but when x is equal to 0, that term, the beta 1 term, disappears. So the log odds for the high group is equal to just beta naught. Given this information, what we'll see is that this setup here is also important for interpretation of model parameters. So you may have to come back and refer to this later on. Well, we'll get to that part more next day, I think. So in the sample, we can use the data to estimate these quantities. So for the low salt group, we would estimate beta naught with B naught and beta 1 with B1. And we know that for the high salt group, when x equals 0, our estimate of beta naught will be B naught. But remember, using the data, we already calculated what p hat high over 1 minus p hat high was, as well as the odds, the odds among the low salt diet group. So what we're going to do is sort of flip this around. Say, well, B naught is equal to this quantity, and so this log odds, and this is something that we calculated from our data. So, just as I said, we put B naught on the left-hand side. It's equal to the log of the odds among the high group. Remember, that's when x is equal to 0 and x is 0 for the high salt diet group. And we calculated on the previous 2 pages ago, on page 159, that odds was 0.098765432. And if you take the ln of that number, you should get minus 2.315 and so forth. For the B1, I'm just going to go back to our previous page. So this is page 160. And remember, we said that if you're in the low group, x is equal to 1, then you get B naught plus B1, and the x is equal to 1, so we don't need to write it. But then we can flip this around and say, okay, well then B1 is simply equal to the log odds for the low group minus B naught. So that's what we work through on page 161. So we have B naught is equal to the log odds for the low group minus B naught. From the data, we were able to calculate the odds to be 0.0814, etc. Minus, here is the B naught we got from up above. And if we work it out, we end up getting an estimate of beta 1, so a slope estimate of minus 0.19329739. So our fitted logistic model is simply the one where we add in or we replace B naught and B1 with their estimated values. So we have our, I've plugged in B naught here, our B1 there, that's our X. And so this is what our actual model is for the cardiovascular disease data. So remember, we're not modeling the mean of the response, we're modeling a function of the mean because the mean is the P as well. So this is a function of the mean. And if we look back up here, we can see B naught is the log odds for the high group. B1 is the difference in the log odds between the low group and the high group. So I'm writing that out just in words down below. That B naught is equal to minus 2.3. That's the estimated log odds of developing cardiovascular disease for the high salt diet group. And B1 is equal, so remember this is kind of like our control group in some sense. B1 is equal to minus 0.1932. This is the estimated difference in log odds of developing cardiovascular disease, comparing the low salt diet group to the high salt diet group. So there we're saying that it's low minus high. The problem with this in practice is the use of the log odds. So even though it's a nice way to come up with our regression model, in practice, the practitioners, they don't often, they have trouble following what we mean by log odds. Because remember, we're trying to think about a distribution, and trying to think of a distribution on the log scale is complicated. So for the logistic regression, when we go to interpret our model parameters, instead of interpreting in terms of B1 and B naught directly, what we do is we use a function of B naught and B1 so that that function or that value tells us about not the log odds, but the odds directly. So next day, I'm going to stop here, but next day what we'll do is look at how you actually go from using an interpretation that uses these logs to not using the logs. Okay, and so that will involve taking the anti-log, so exponentiating each side, but we will look at that next day. So let me add that to the bottom. Next day. Okay, so I'm going to upload, after I upload this video, I'll also work on trying to give you a little bit of a review, but I'll make that into a separate video that can be uploaded on its own or viewed on its own. All right, so I guess I will see you guys or talk to you on Friday test time. Good luck to everyone. Email me if you have any problems during the test or after the test when you're trying to upload or anything. All right, talk to you then, or I will talk to you on Monday.